Hello, I'm Norman Wildberger. Today we want to have a look at the algebra of 2 by 2 matrices, which is an all-encompassing arena for this non-commutative algebra, incorporating, ultimately, the complex numbers blue, red, and green that we introduced last time, and providing a sort of unifying framework for these three different types of geometry that we ran across when we were talking about relativistic geometry and Euclidean geometry. So, the 2 by 2 matrices, it's a linear space. Here's how we add two of them. Here's how we scalar multiply a matrix by a scalar. We talked quite a lot about 2 by 2 matrices in our earlier part of the course, while in Algebra 6 and 7, so you might want to review those two lectures. This is a four-dimensional space. It's another interesting example of a four-dimensional space, and we can see that it's four-dimensional because it has this explicit basis consisting of these four matrices, which we might call E11, E12, E21, and E22. It's pretty obvious that they're linearly independent and that they span the space. But now today we're going to concentrate on something in addition to the linear structure, which is the multiplicative structure. The fact that we can multiply 2 by 2 matrices. Okay. This makes it a very rich arena, but in addition there are some other things that are floating around that are also quite interesting. In particular, these important functions that are going to be called trace and determinant that play a crucial role in understanding this algebra. Okay, so the idea is we're going to look at this algebra sort of more broadly, and inside are these various complexions that we were talking about before, and the relativistic rotations and Lorentz boosts and so on are all living inside this 2 by 2 matrix algebra. It's a very important mathematical object. All right, so let me remind you what the multiplication is. Of course, it's very familiar, I hope. Here's two 2 by 2 matrices, and here is how we multiply them. So this entry here is this row times this column. This entry here is this row times this column, and so on. So that's how we multiply matrices, and then we've seen that this multiplication satisfies some properties. The associative law for multiplication, the distributive laws connecting the multiplication and the addition, and then this other form of a kind of an associative law or distributive law, depending on how you think about it, that says that A times lambda B is the same as lambda A times B is the same as lambda times AB. And then there were some special matrices that we pointed out in our earlier videos. Obviously the zero matrix and the identity matrix, often denoted by I. And then at some point we also introduced these three other matrices, which at that point we called G, R, and B. Perhaps it wasn't so obvious why we called them that, but now it's perhaps a little bit more clear. So G, R, and B are the other matrices that together with I form a basis, and they're intimately connected with the green, red, and blue geometries. In fact, in our last video we called them something else. So this G was actually called K, and this R was called J, and this B, well actually its negative, was called I. So a slight renaming in the context of complex numbers and such things. It's more usual to think in terms of this matrix being called 1, this one being called I, this one J, this one K. So this is another basis for this four-dimensional space of 2 by 2 matrices. Okay, so we want to give a name to this kind of structure that is exhibited by the 2 by 2 matrices. It's a linear space with a multiplication satisfying some reasonable arithmetical laws. And we're going to call this thing an algebra. Now the word algebra, of course, already has a prior meaning. So this is a different usage of that term. It's a rather specific term in this context that just refers to a linear or vector space together with a multiplication and an identity element, I, which satisfies basically the properties that we've just mentioned. It's basically distributive over addition. Both on the left and the right hand side. It's distributive with respect to scalar multiplication. So here's another way of saying that law, that lambda A times mu B is equal to lambda times mu times AB. And it's associative. The multiplication is associative. And finally, the identity element I acts the way you would expect, namely I times A is A, and A times I is A for any element in the space. All right, and the main example that we're focusing on here are the 2x2 matrices. And in fact, it's not hard to see that we can generalize that very easily to the n by n matrices, having exactly the same properties. Now, we haven't said it, but this situation is also non-commutative in the sense that multiplication of matrices is generally non-commutative. Sometimes AB equals BA, but most of the time those two things are different. So that's a big difference between the commutative kind of arithmetic that we have with normal numbers and polynomials, say. All right, so that's what we mean by an algebra here, and we're really going to be focusing on this particular one, the 2x2 matrices. But in general, we can say that if A is an algebra, then a subalgebra B inside A is a linear subspace of A, which is itself also an algebra with the same multiplication and identity element I. All right, so this is a very important notion. If you have an algebraic structure of any kind, then generally it's important to identify what we mean by substructures. Okay, and here the idea is we have an algebra, typically this one here. Then if we have a subspace, which is also essentially closed under multiplication and contains the identity element, then we're going to say that that's a subalgebra of the algebra A. So B inside A is a subalgebra. All right, so let's have a look at subalgebras of our algebra of 2x2 matrices. The only one-dimensional subalgebra is consisting of multiples of the identity matrix. Because the identity matrix has to be in a subalgebra. We've agreed by convention that that's going to be true. And so, since we have a linear subspace, it has to be closed under scalar multiplication. So multiples of the identity, in other words, matrices of this form, lambda, 0, 0, lambda, have to be in there if we're having a one-dimensional subspace, and that's all there can be, because that's already a one-dimensional subspace, and it's a subalgebra because if you multiply any two matrices of that form, you're going to get another matrix of that form. So that is indeed a subalgebra, and it's the only one-dimensional subalgebra. In terms of two-dimensional subalgebras, we've already seen three very important ones. Things we called blue complexions, red complexions, and green complexions. All right. So the blue complexions are all the 2x2 matrices of the form AB minus BA. The red complexions are all the matrices of the form AB, BA. And the green complexions are all the matrices of the form A0, 0B. And we've seen that each one of these separately is a subalgebra because it's closed under multiplication. And they're obviously all linear spaces or linear subspaces. If we add any two matrices like this, we're going to get another one of this form. If we multiply this matrix by a scalar, we get another matrix of this form. That means that this is a linear subspace. Similarly, this is a linear subspace, this is a linear subspace, and in addition, each one of them is closed under multiplication and contains the identity element. Right? The identity element is a special case when A is equal to 1 and B is equal to 0 here. A is equal to 1 and B equal to 0 here, and A and B both equal to 1 there. But there are some other two-dimensional subspaces, which are in fact subalgebras. Two very important ones are what we might call n plus and n minus. N plus are the upper triangular matrices. Matrices which have A's on the diagonal and B in the upper right corner and 0 in the bottom left corner. That's a subspace. If you add any two such matrices, you get another one of that form. If you multiply one by a scalar, you get another one of that form. But in addition, this is also a subalgebra, that if you multiply two such matrices, you get another one of this form. Please check that to make sure that it's true. And similarly, this one here, which is sort of symmetrical to this one, is also a subalgebra. And both of them are two-dimensional because they essentially depend on two parameters, A and B. We could easily write down a basis. A basis for this space would be the matrix 1, 1, 0, 0, the identity matrix, and the matrix with entries 0, 1, 0, 0. Those two matrices would be a basis for this, so it really is a two-dimensional space. All right, so here's an exercise for you, a little bit of an interesting exercise. Show that we can create other two-dimensional subalgebras in the following way. That if we take any matrix A, which does not belong to this diagonal subalgebra of multiples of the identity. So if you take any matrix A which is not a multiple of the identity, and then you form a subspace by looking at matrices of the form lambda times the identity plus mu times A. Lambda and mu are arbitrary scalars or rational numbers. So you have to show that matrices of this kind form a two-dimensional subalgebra of our 2 by 2 matrices. And they are all of this form. So in other words, any two-dimensional subalgebra is of this form for some matrix A, which is not a multiple of the identity. So this is a characterization of all the two-dimensional subalgebras of our 2 by 2 algebra of matrices. So these are just special cases of this more general setup. All right, now let's look for some three-dimensional subalgebras. All right, so here are two examples. Let's call them B plus and B minus. B plus consists of matrices of the form A, B, 0, D. So it's a lot like N plus, except that with N plus, these two entries had to be the same. Now they're allowed to be different. So we actually have a three-dimensional space now. And in fact, that's actually a three-dimensional subalgebra. If you multiply two such matrices, you're going to get another matrix of the same kind. Please check that. All right, please check that it's a subalgebra. And similarly, B minus, matrices of the form A0, C, D, form a subalgebra. So our next exercise, a little bit maybe more challenging. Can you describe all three-dimensional subalgebras? Can you sort of organize some way of understanding all three-dimensional subalgebras of our four-dimensional algebra of 2 by 2 matrices? And finally, our last, perhaps most obvious subalgebra is that A itself is the only four-dimensional subalgebra. So we are allowing the whole algebra to be included as a subalgebra. That's standard terminology in mathematics. The big object itself can also be thought of as a sub-object of itself. Okay, so we have an interesting arena for arithmetic now. We have this 2 by 2 algebra of matrices. And we have addition, multiplication. We have scalar multiplication. One thing that we like to do generally is to ask, well, when can we divide? When can we have invertible elements? So let me remind you that if you have a matrix A, consisting of the 2 by 2 matrix A, B, C, D, then it has an inverse matrix, A inverse, of this form, precisely when the determinant is non-zero. So this determinant is the quantity AD minus BC. If that quantity is not zero, then this matrix is invertible. It does have an inverse, and here's the formula for its inverse. So we have a factor out front which has 1 over that determinant out front. And then the matrix that's appearing here is an interesting sort of twist on the original matrix, obtained by swapping the two diagonal elements and multiplying the off-diagonal elements by -1. So that's unfamiliar. Please review the earlier lessons on 2 by 2 matrices and their inverses. Just to alert you, this matrix here is going to play an important role a little bit later on in the lecture. We're going to end up calling this A star, sometimes called the adjugate of the matrix A. Now there's an important remark to be made here. Okay? So the general idea that a matrix is invertible when its determinant is non-zero is valid for higher dimensional matrices too, as we've seen. Okay. But there's something special that happens in the 2 by 2 case. That doesn't happen in the 3 by 3 case, it doesn't happen in any of the higher dimensions, which really contributes to making the 2 by 2 algebra very, very special and unique. Okay. And it's this simple but very important fact, that in the 2 by 2 case, the determinant, this quantity AD minus BC, is a quadratic expression. So this condition for being invertible is a quadratic condition. If you go to 3 by 3 matrices, it becomes cubic. 4 by 4 matrices, it becomes degree 4. Only in degree 2 is it a quadratic condition. We're going to see that there's something very special about 2 by 2 matrices, and this is certainly part of that, maybe a very important contributing aspect to the special nature of the 2 by 2 algebra of matrices. It might be a good place to pause just momentarily and say a few sort of philosophical words, or sort of large-scale words. So there are really levels of arithmetic, and a large part of mathematics can be framed in terms of thinking about levels of increasing sophistication for doing arithmetic. When we start out learning mathematics, we start with the natural numbers or counting numbers, and then we progress to the integers, and then a little while later we learn about the rational numbers. In high school, then we move to polynomials, and polynomial arithmetic becomes very important. Then sort of more at the university level, we start to learn about power series and matrices. So we're talking about matrices here now, and you can think about these as all sort of different levels of arithmetic, where we're moving to arithmetic with larger, more complicated objects, where the arithmetic becomes more intricate and involved. And often we end up including the lower levels sort of inside what we're doing. After matrices, we might think of infinite matrices, which sort of play perhaps a similar role to matrices as do power series to polynomials. So in this list already, we have a good majority of modern mathematics is represented one way or the other. Geometry, algebra, number theory, a lot of analysis, even differential geometry, Lie theory. A lot of mathematics is frameable in this context. Operator algebras, von Neumann algebras, a lot of things are really in this domain. So a very big lesson that you should keep in mind is that matrix algebra is very rich. When you go from arithmetic with natural numbers and rational numbers to arithmetic with matrices, it's a very, very big jump. Okay, things are much bigger and richer. And one big aspect of that is that we're moving from generally commutative situations, where the multiplication doesn't depend on the order, to non-commutative arithmetic with these matrices. Okay? That's a very big source of the complexity and richness of this domain. So it's one of the reasons also why linear algebra is such a fundamental subject, is because it's linear algebra that provides us with the essential tools for understanding these big areas of arithmetic ultimately. It's an arithmetic which is intimately connected with geometry. Let me remind you of a few other important aspects of 2x2 matrices. Let me remind you about the trace, the determinant, which we've already talked about, and the characteristic polynomial. This goes back to our discussion in Wildberger Algebra 12 of eigenvectors and the associated eigenvalues. So the equation A times V equals lambda times V is sometimes called an eigenvector equation, or the eigenvector equation for A. So a vector V is an eigenvector for A if it satisfies this equation for some scalar lambda. In that case, this number lambda is called the associated eigenvalue for the matrix A. Now, when we're looking for eigenvectors and looking for eigenvalues, it turns out to be convenient to rearrange this equation in the form AV minus lambda V equals 0, or A minus lambda I times V equals 0. And that has a solution precisely when determinant of A minus lambda I equals 0. So this is sort of an auxiliary equation that comes from this one that allows us to look for the eigenvalues in terms of a polynomial equation. This is called the characteristic equation of the matrix A. And its zeros, if it has any, are the eigenvalues of A. And let me remind you what happens specifically in the 2x2 case, which is simple, relatively simple. If we have a matrix A whose entries are little a, b, c, and d, then the characteristic equation for A is this one, determinant of this matrix minus lambda times the identity. It means we're subtracting lambda from the diagonal of the matrix and taking the determinant of that and setting it equal to 0. Well, this determinant is A minus lambda times D minus lambda minus BC equals 0. And then if we look at this and write it as an equation, a polynomial equation in lambda, we get lambda squared minus A plus D times lambda, and then the constant terms AD minus BC, all equal 0. So this is what the characteristic equation looks like for a 2x2 matrix. And once you've seen it, you can write down the characteristic equation immediately. The coefficient here of the lambda is minus the trace. A plus D is called the trace of A, denoted by TR abbreviation. And this quantity AD minus BC we recognize as being the determinant of A. All right, so the characteristic equation notably involves the trace, actually with a minus sign there, and the determinant. And conversely, if you know what the trace and the determinant is, you can immediately write down that characteristic equation and look for eigenvalues. And I remind you that the determinant has sometimes some different notation. So sometimes the determinant is written det of the matrix A, and earlier we used this alternate notation with a delta or triangle to denote the determinant. And let me remind you of the most important fact about the determinant. Its multiplicative aspect. That the determinant of a product of two matrices A times B is the product of the determinant of A times the determinant of B. Or in this language, determinant of AB equals determinant of A times determinant of B. We talked about that in Wildberger Algebra 5. Let's have a look at a corresponding sort of important property of the trace. All right. So this is what we might call the symmetry of trace theorem, which says that the trace of AB equals the trace of BA. The matrices AB and BA are in general not the same, but this theorem asserts that their trace, the sum of the diagonal elements, is the same. A proof is a direct computation. If A is the matrix A, B, C, D, and B is the matrix A prime, B prime, C prime, D prime, well then the trace of AB is the trace of, here's the product of A times B. And here is the product of B times A. And the trace here is this plus this, and the trace over here is this plus this. And you can see that they add up. There's an AA prime here and here. There's a BC prime here and here. There's a CB prime here and here, and a DD prime here and here. So if you add this element and this element from AB, you get the sum of this element and this element from BA. That's a very important property of the trace. Trace of AB equals trace of BA. Alright, so in today's lecture we've introduced the algebra structure of 2x2 matrices. We've looked at some important subalgebras, and I've reminded you of some important facts relating to eigenvalues and eigenvectors, relating to trace and determinants of 2x2 matrices. Time for an exercise. And this is a very important exercise and probably an interesting one too. So this exercise will pave the way for our next lecture, which will be a continuation of this study of the algebraic aspect of 2x2 matrices. Okay, so what we're going to do is we're going to see that the 2x2 algebra of matrices has a dot product. Okay? It's very much like the dot products that we've been talking about, but not dot products between two vectors, a dot product between two matrices. Okay, it's a very fundamental concept. And in fact, it turns out that there are at least three interesting and pretty natural dot products that appear on this algebra of 2x2 matrices. One of them is going to be a lot more important than the others for our purposes. They're all interesting though. And I want you to explore these three dot products and check, in fact, that they are indeed symmetric bilinear forms. So the first one, if we define the dot product on A, which is our algebra of 2x2 matrices, in this way, that A dot B equals trace of AB. All right, so you have two matrices A and B. To form their dot product, you multiply the two matrices and take the trace. So you have to show that this is a symmetric bilinear form. And then I want you to do the same for a slight twist. If we define the dot product in this way, that A dot B is trace of A times B transpose. Got to remind you that the transpose of the matrix A, B, C, D is the matrix A, C, B, D, obtained by essentially reflecting along the diagonal. So the B and the C interchange, but the A and D stay where they are. So check that that's also a symmetric bilinear form. And now the third one, which is going to be the most interesting and most unique one for us. Do the same thing for this. For A dot B is defined to be the trace of A times B star, where here is the star of the matrix, and this is sometimes called the classical adjoint. Sometimes also called an adjugate. Here's the definition. A, B, C, D star is D minus B minus CA. I hope that looks familiar. That's exactly the matrix that's involved in the inverse of this matrix if this has an inverse. So if you look back to the formula for the inverse of this matrix, if its determinant is non-zero, is exactly this matrix with a factor 1 over the determinant in front. Right? So this matrix here, which is basically a matrix of cofactors of the original matrix, is called the adjugate or the classical adjoint. And it has different notation. This is not always standard notation, but it's going to be useful for us. So we're going to use this star to mean the adjugate or the classical adjoint. So you have to show that if you define a third dot product by A dot B is trace of A B star, then you also get a symmetric bilinear form. So we have actually 3 dot products on the 2 by 2 matrices, but it turns out that this one is very special. Okay? These 2 dot products work for any dimension. They live on 3 by 3 matrices, 4 by 4 matrices, and so on. This one only lives in the 2 by 2 world. It's very special. And we're going to see that it's really this one here that allows us to bring together the chromatic aspect of this algebra of 2 by 2 matrices in a very rich and beautiful structure. To prepare for that, I do suggest that you have a look at my series of videos, Famous Math Problems 13, which is on the rotation problem and quaternions. Okay, so that's a quite involved series, but it's highly algebraic, highly linear algebraic, and it'll be a very good sort of complement to what we're doing here. So we're going to be talking about this inner product on the algebra of 2 by 2 matrices next time, and how it relates to these 3 complex number systems that we've defined, the blue, red, and green complexions. Interesting stuff. Not entirely standard, so you're not going to find this material easily in standard texts, but still very core kind of material, because it's 2 by 2 matrix algebra. It's the simplest kind of non-commutative mathematics. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.